put here in this is central endocrine organs, and these ones are peripheral endocrine organs. And I've said central endocrine organs, some of them regulate the peripheral endocrine organs. Among the central is hypothalamus, which is part of the brain, just below the thalamus. It originates from the diencephalon. We have the pineal gland also originating from the diencephalon, and the pineal gland is in the roof of the third ventricle. We have the hypophysis occupying the hypophyseal fossa in the sphenoid bone. That is the hypophysis. That is also connected to the brain, to the hypothalamus. Then the peripheral, we have the thyroid gland in the neck region, around the thyroid cartilage, thyroid and cricoid cartilage. We have the parathyroids, which are just posterior to the thyroid, and enclosed within the capsule of the thyroid. Then we have the thymus. If you remember, we have done the thymus before when we are looking at the immune system. The thymus is in the anterior mediastinum within the thorax. Then we have suprarenal gland above the kidneys, the suprarenal above the kidneys. Each of the kidneys will have a suprarenal gland. And then the isolates of Langerhans, that is in the pancreas. So the isolates are part of the pancreas, but they are the endocrine part of the pancreas, and they are isolates, they are islands. They look like islands within the exocrine pancreas. We'll be looking at the details. And then we have the gonads, both the testes and the ovary. Apart from this, we also have what I consider as diffuse neuroendocrine system. Diffuse neuroendocrine system comprises of either a cluster of cells or individual cells which secrete hormones. And these are in various parts. They are in the respiratory system, the respiratory tract. They are also in the digestive tract, quite a lot of them in the digestive tract. We have them in the heart, we have them in the kidney. So these ones are cells which secrete hormones. They secrete hormones, but are either as individual cells or groups of cells. Where there are groups of cells, we can call them neuroendocrine bodies. The neuroendocrine bodies, we use the word neuro because these ones originate from the neurocrest cells. So these are the organs we are going to look at in terms of their structure. Now, we know that hormones, usually we have regulatory mechanisms, and hormones are produced by the glands. They are transported by the blood. Some of the hormones from the central endocrine system, that is from the hypothalamus and the hypophysis, are transported to the blood to the target organs. Those target organs now produce hormones. These hormones then can have a feedback mechanism so that you don't have excess production of the hormones. Occasionally, you might have excess production of hormones when you have tumors or hyperplasia of the organs, overgrowth of the organ. Then in that case, you'll have excess production. But the normal mechanisms are such that the hormones that have been produced influence those particular cells which produce the hormones. These we refer to as feedback mechanisms. So we have the direct feedback mechanisms and indirect feedback mechanisms. In the direct feedback mechanism, we have either long loop or short loop. Let's take a case of a hormone being produced by the hypothalamus. So the hormone being produced by the hypothalamus will influence the hypophysis. The hypophysis produces a hormone. That hormone then goes to negatively influence those cells that produce the hormone from the hypothalamus. So they have negative feedback mechanisms. We have cells within the hypothalamus and hormones produced by the hypothalamus that are inhibitory. So this is a short loop, and then for the long loop, where we have the target organs, let's say the testis or the ovary, produces the hormones, and those hormones can influence the hypothalamus, which is supposed to be stimulating the production of those hormones by the hypophysis. So this is an indirect long loop, whereas the direct short loop, long loop, the direct short long loop is where we have those hormones from the target organs, like the ovary or the testis, directly influencing the hypophysis so that those hormones stop being produced. For example, you can have follicle-stimulating hormone being produced by the hypophysis. It stimulates the development of the follicles within the ovary, and those follicles then produce a hormone, estrogen. The estrogen then negatively inhibits production of further follicle-stimulating hormone, so that we don't have excess production of the hormone. Or the estrogen will inhibit the releasing hormones, gonadotropin releasing hormone, which is supposed to stimulate those cells that produce follicle stimulating hormone. That is now in the indirect long loop. And then the ultra short loop is where we have the hormones negatively influencing directly from the median eminence, as we'll be able to see. So these are negative feedback mechanisms. We also have positive feedback mechanisms. In the positive feedback mechanism, a good example is oxytocin. Normally, oxytocin influences the milk letdown and also contraction of the uterus. So during lactation, when the baby is suckling, then neural stimulation of the nipple gives a feedback to the hypothalamus, and then the hypothalamus produces more oxytocin so that you can have more milk being produced. Similarly, when the baby is at the cervix, the head is at the cervix during delivery, the pressure applied to the cervix, nerve endings from that particular part will give a feedback mechanism so that you have more oxytocin being produced so that the uterine wall can contract to push the baby out. Those are positive feedback mechanisms. The rest are negative feedback mechanisms. Let's now look at the structure of the general endocrine organ. It's an organ. So like all the other organs, they are normally solid organs, and they have a lot of connective tissue. The first connective tissue is what covers the organ, that we refer to as a capsule. That's a fibrous connective tissue, dense fibrous connective tissue. This is to protect the organ. That dense fibrous connective tissue penetrates into the organ either as a septa with a very thin penetration or trabecular. And this may divide the organ into lobes and lobules. We'll be seeing that case in the case of the thyroid gland, a very clear case. Also, the connective tissue, which is now the stroma, supports the nerves, the blood vessels, as they enter into the organ. And the area where these structures enter into the organ, the neurovascular bundles, is what we call the hilum, or the hills of the organ. And then we have the parenchyma. The parenchyma are the cells that are actually secreting the hormone. So those cells secreting the hormone are usually arranged in either clusters, a cluster of cells, or clumps of cells, or sometimes in codes. Can be 2 layers of cells forming a cord, or 3 layers of cells forming a cord, as long as each of those cells is close to a blood vessel. They might also form some nest-like structures, or they might be anastomosing cords. So these cords join each other to form a network. That's what you're calling anastomosing cords. In between these cords, we have blood vessels. So we have a very well vascularized network of blood vessels, and this comprises of sinusoidal capillaries or fenestrated capillaries. Because the molecules that are being released, the hormones that are being released, are very large, they cannot pass through a continuous capillary. So those which are smaller will pass through fenestrated capillaries because they are window-like apertures that allow the passage of the hormone into the blood vessels to onward transport to the target organs. So this is the general structure that we will not be talking about. Again, each of those will have a capsule, will have a septum, will have a trabecula, it will have the parenchyma cells, and the vascular network. Apart from this, of course, we have the ground matrix, in which the cells and the fibers are suspended. Now, as we look at these cells, as we look at the hormones, we need to understand what is the biochemical nature of these hormones. Because we are going to describe the cells that produce these hormones. We are going to look at those organelles that produce the hormones. So we must understand what is the chemical nature of the hormones. Hormones are of various types. They can be peptides, and these are amino acid derivatives from proteins. Among the peptides, we have the adrenocorticotropic hormone released from the pituitary gland, oxytocin, antidiuretic hormone, also called vasopressin, released from the neurohypophysis, but actually produced by the hypothalamus. We have the somatostatin hormone, produced by the pancreas, the glucagon hormone, the insulin, all these are produced by the pancreas. We have calcitonin, produced by the C cells of the thyroid gland. We have the parathyroid hormone, and then produced by the parathyroid gland. And then we have atrial natriuretic peptide, also called atrial natriuretic factor, which is produced by the cells of the heart. So these are peptides in nature. So we know what peptides are. We are going to eventually look at those organs, and that as we describe them, we are going to look at the organelles that synthesize those peptides. The others are proteins, protein in nature. The growth hormone, which is very important in growth of muscles, growth in bones. So the growth hormone is a protein in nature. And then prolactin. Prolactin, also all these two are produced by the hypophysis. Growth hormone and prolactin are produced by the hypophysis. Prolactin that is very important in the development of the mammary gland. The other ones are glycoproteins. Remember, this is a glycoprotein which is having carbohydrates, oligosaccharides, and proteins combined. Carbohydrates and proteins combined. And usually these are combined by the Golgi apparatus. So we'll have very well developed Golgi apparatus. In this particular organs that have the cells that secrete these particular hormones. The thyroid stimulating hormone, which is from the thyroid gland, the luteinizing hormone, and follicle stimulating hormone. These ones are from the hypophysis. Erythropoietin, which is produced by the kidney, cells of the kidney. So these are glycoproteins. Being glycoproteins, you can stain for them to demonstrate carbohydrates by periodic acid shift. Then we have the steroid hormones. Steroids are derived from the cholesterol, and usually most of these are produced by the cortical part of suprarenal gland, comprising of the glucocorticoids, cortisol, aldosterone, mineralocorticoid, and gonadal hormone, which is dihydroepiandrosterone. Also, testosterone and estrogen, testosterone from the male testis and estrogen from the ovary, and calcitriol, or the active vitamin D, so from the kidney. So these hormones are steroid in nature. They are not normally in a follicle form, and they are not in vesicles within the cell. They appear as lipid droplets. So they are not membrane-bound secretory vesicles. So we need to note, as we describe these cells, we'll be able to understand why they appear the way they do. The other ones are amines, indole amines like melatonin, melatonin, serotonin. Those are referred to as indole amines. The other amines are these are tyrosine derivatives, dopamine, epinephrine, norepinephrine. Epinephrine or epinephrine produced by the adrenal medulla, melatonin produced by the pineal gland, and T3, T4, this is thyroxine, which is produced by the thyroid gland. So these are the hormones that are amine, that are derived from tyrosine, and we'll be looking at the structure of this. So these are the nature of the hormones. So we need to understand this to be able to describe the cell and the content of the cell in terms of the organelles. Now we have specific hormones and cell organelles. Let's just look at this as a summary form. We have the amines. Those that produce the amines, these hormones here, are produced, the cells that produce this will be very rich in mitochondria and smooth endoplasmic reticulum. Mitochondria and smooth endoplasmic reticulum. Some of the final enzymatic activity for the production of the hormones occur within the mitochondria. Thyroid hormones, the cells are normally very large, polygonal cells. They are eosinophilic staining, so they stain for acidic dyes. That's why it's eosinophilic, with very active chromatin within the nucleus. They are pale staining. Pale staining because during preparation, when you use H&E, usually the lipid within the cell is removed with the alcohol, and therefore those parts appear as pale staining. And because of that, the areas where the lipids are will appear as empty vacuoles. So the cytoplasm appears vacuolated. In these particular steroid secreting cells, they have very well developed smooth endoplasmic reticulum. very well developed smooth endoplasmic reticulum, and mitochondria that have a tubular crystal. You know the crystal of the mitochondria, they can be rod-shaped, but these are tubular in nature. So the mitochondria is where the final breakdown formation of the hormone actually takes place. Golgi apparatus is very poorly developed. So this is wrong spelling, poorly developed because the hormone is not in a vesicle form. The hormone is in lipid droplets because it appears as lipid droplets. So the proteins, these are the same as the peptides secreting cells. They are very well developed rough endoplasmic reticulum, and because of that, they are basophilic in staining. They stain very deep basophilic. The rough endoplasmic reticulum is for synthesis of proteins. Ribosomes are attached to rough endoplasmic reticulum. We have the Golgi apparatus. Golgi apparatus for the final packaging and also provision of the vesicle. And mitochondria, just like what we had said before, where we have final production of the provision of the energy. The peptides, the cells are usually polygonal or columnar shaped and are basophilic. Just like what we have in canine form, they are basophilic. Basophilic because they have well-developed rough endoplasmic reticulum, the ribosomes. They also have Golgi apparatus, mitochondria, and microtubules. Remember, microtubules are very important in intracellular transport. Apart from this, we also have some common organelles. Some of the common organelles will include the Golgi for packaging, mitochondria, microtubules, and intracellular transport. Mitochondria to provide the motive the energy, and also we have the mitochondria, sometimes enzymes are located within the mitochondria. They are of different shapes. We have talked about polygonal cells. Some of them appear cuboidal, like in the thyroid gland. They are polygonal, like in the suprarenal gland. Most of the steroid producing are polygonal. They could be columnar, like in the parathyroid gland, or they can be stellate in shape. What we say in the pineal gland, where the cell has several processes that produce melatonin. So there will be different shapes, and these cells are attached together by junctional complexes. And each cell is exposed to a blood vessel, very close to a blood vessel, because the hormone is supposed to be transported by blood. Now, for biological origin of these endocrine organs, they come from all the germ layers. In a summary, they all come from all the germ layers. I'll just mention each of those and which ones come from what, but overall, they come from all germ layers. The hypothalamus is neuroendocrine, it's from neuroectoderm, from the diencephalon. The pineal gland is a neural ectoderm. Remember, the ectoderm eventually divides into surface ectoderm and neural ectoderm. The neural ectoderm developed to form the nerve tissue and neurocrest cells. The cells between the neural ectoderm and surface ectoderm will be referred to as neurocrest cells, and then the rest of the cells will form the epidermis. The hypophysis comes from two sources. There's a neural ectoderm, the neurohypophysis from the diencephalon, and then the glandular part, the adenohypophysis, is from the oral ectoderm. And this is from the rat case pouch. Evagination of the oral ectoderm, forming rat case pouch. And then this rat case pouch migrate towards the neural ectoderm, and fuse together now to form the gland that we refer to as the hypophysis. The neural ectoderm retains its conduct to the brain. The adenohypophysis does not retain its conduct to the oral cavity. The thyroid gland is from the third pharyngeal pouch, so it is endodermal in origin. The suprarenal gland, the cortex, is from the mesoderm, splanchnic mesoderm. The medulla is from the neural ectoderm as migration of the neurocrest cells. So medulla is of neurocrest origin. The pancreas is from the foreguard endoderm as evagination of the endoderm at the distal part of the duodenum. The parathyroids, we have two parathyroids. We have the superior parathyroids from the fourth pharyngeal pouch, the inferior parathyroids from the third pharyngeal pouch. The gonads are from the intermediate mesoderm, formed from the gonadal ridge. Diffuse neuroendocrine system, most of the cells secrete peptides and there are neurocrest derivatives. So they originate from the neural ectoderm. So you can see that we have cells from the ectoderm, we have cells from the mesoderm, and we have cells from the endoderm. Let's now look at the hypothalamus. The hypothalamus is a part of the brain below the thalamus, and the roof of the hypothalamus is formed by the third ventricle. So that is the roof of the hypothalamus. So the hypothalamus actually not the roof, but is surrounded. The hypothalamus surrounds the third ventricle. The hypothalamus, for the endocrine purpose, will be looking at the hypothalamus again under the nervous system. But for endocrine purposes, the hypothalamus have several aggregates. It's nerve tissue, but these are specialized secretory neurons. They are secretory neurons. They are not myelinated. Because they don't transmit an impulse. The cell bodies of these neurons aggregate to form some nuclei. Aggregates of cell bodies in central nervous system, we call the nuclei. So we have two types of nuclei. We have those with very large cell bodies that we call magnocellular nuclei. These are the two. We have paraventricular adjacent to the ventricle. These ones have very large cell bodies. And then supraoptic nucleus above the optic chiasma. These secretory neurons secrete two hormones, oxytocin and vasopressin. The hormone is then transported from the hypothalamus, from this nuclei, to the neurohypophysis. So the axons extend all the way from the hypothalamus to the neurohypophysis, where the hormone is released, stored and released. The hormone is in a form of, within the cell, we have visible structures that we call the herring bodies. Herring bodies contain the hormone, and the protein called neurophysin is very important in that transport of the hormone to the neurohypophysis. So this is by exoplasmic flow. We'll be looking at the neurohypophysis. The other cells, the other nuclei, have small cell bodies. Small cell bodies. So we call them parvocellular. Parvocellular. This includes ventromedial nucleus, dorsomedial nucleus, we have the infundibular nucleus, the tubal nucleus. These nuclei have small cell bodies. Again, those neurons are secretory. They secrete releasing hormones. These releasing hormones are transported by very short axons to the median eminence, where we have the primary capillary plexus. So they are released at the primary capillary plexus. The primary capillary plexus pick up those hormones, also called releasing hormones or inhibiting hormones. The releasing hormones are also referred to as liberins. The inhibiting hormones are referred to as statins. So the primary capillary plexus picks it up, transports it to the adenohypophysis through the hypophyseal portal system. So we have portal veins that transport the hormone to the adenohypophysis. The hormones then leave the blood vessels and stimulate the cells within the adenohypophysis. And those cells now produce hormones which are transported to the target organs. So this is what we have as the hypothalamus, magnocellular and parvocellular nuclei. So we have talked about the hypophysis, and the hypophysis has two parts: adenohypophysis from the Rathke's pouch. You can have three parts of the adenohypophysis. We have a pars tuberalis that come to surround part of the infundibulum, the neural part. Then we have pars intermedia between the neurohypophysis and the adenohypophysis, where both neural tissue and glandular tissue are mixed together. We have pars distalis, which is the largest part of the three parts. We have the median eminence. In the median eminence, this is where the capillaries lack a blood-brain barrier. So the hormones can get in very easily into the blood at the median eminence. And then the infundibulum, which is the stalk that connects the distal part of the neurohypophysis to the hypothalamus. And then pars nervosa. The pars nervosa is a large part where we have the storage of the oxytocin and vasopressin, and also release of that part. So this is to illustrate in a nutshell the connection between the hypothalamus and the hypophysis. For the neurohypophysis, we have the hormones, supraoptic nucleus and paraventricular nucleus, which are large cell bodies, magnocellular, release the hormone oxytocin and vasopressin. It is transported through this hypophyseal tract to the pars nervosa, where the hormone is released into the blood. Then we have the parvocellular. These are small cell bodies. They pick the hormone The hormone is synthesized in the cell body. It is transported and released at the median eminence to the primary capillary plexus, and then from the primary capillary plexus, those releasing or inhibiting hormones are then transported to the adenohypophysis by the hypothalamo-hypophyseal portal system. And then at the secondary capillary plexus, the hormone is released and stimulates the cells within the hypophysis now to produce hormones. Among the hormones produced are prolactin, that is very important in development of the mammary, that are very important in the development of bones, muscles, and adipose tissue. We have luteinizing hormone, very important in the release ovulation, and also very important in secretion of testosterone in the testes. We have follicle stimulating hormone, very important in the development of the follicles in the ovary, and also very important in the functioning of the Sertoli cells within the testes for the production of spermatozoa. Thyroid stimulating hormone is the thyroid gland that now secretes the hormone thyroxine. Adrenocorticotropic hormone that stimulates adrenal cortex. And then oxytocin and ADH, which we talked about. Oxytocin to the uterus for contraction of the uterus, and then stimulation of the epithelial cells within the mammary gland for milk letdown. Apart from this, it also supplies the testes, the smooth muscles within the testes for the transportation of spermatozoa. And then antidiuretic hormone in the kidney that is very important in reabsorption of water for the concentration of urine. So this is a very important connection between the hypothalamus and the hypophysis. Hypophyseal axis, but if it goes to the uterus, ovaries and testes, then we refer to it as hypothalamo-hypophyseal gonadal axis. Hypothalamo-hypophyseal gonadal axis. This is the hypothalamus. This is the infundibulum that connects it. This is now the pars nervosa and pars distalis of the hypothalamus. Hypophysis, sorry. Now, for the development of hypophysis, we are from the diencephalon and also from the hook of this oral cavity at Raschke's pouch. So this continues on. Eventually, this detach from the roof as Raschke's pouch and come to lie close to where we have the hypophysis, and where the two cells are very closely together, the cells mix up. So the adenohypophysis now comes to form the pars tuberalis, pars intermedia, and pars distalis. Note connection, continuous connection by the infundibular stalk to the hypothalamus. Note also the formation of extension that comes to end all of this as pars tuberalis, pars intermedia, and pars distalis. In the pars intermedia, we have some colloid remnants. For the hypophysis, also called pituitary gland, we have this is the neurohypophysis, this is the pars intermedia, this is pars distalis, and then the pars tuberalis. This is the infundibulum. For the cell structure, of course, the hypophysis is covered by a connective tissue capsule. And usually we can group the cells into those that take up stains that we refer to as chromophils, and those that do not take up stain that we refer to as chromophores. Among the chromophils, we have the acidophils that have affinity for acidic dyes, and basophils that have affinity for basic dyes. Among the acidophils, these cells we call somatotropes that produce growth hormone under the stimulation of somatotropin-releasing hormone from the hypothalamus. We have the mammotropes, that's very important in mammary gland, that we have mammotropin-releasing hormone from the hypothalamus stimulating the mammotrope cells. These are acidophils. And then for the basophils, we have gonadotropes that are stimulated by gonadotropin-releasing hormone from the hypothalamus. Thyrotropes stimulated by thyrotropin-releasing hormone from the hypothalamus. These ones are from the parvocellular nuclei of the hypothalamus. Parvocellular nuclei of the hypothalamus. We have the corticotropes that produce corticotropin-releasing hormone from the hypothalamus. These are releasing hormones, also referred to as liberins. At the same time, when we have the negative feedback mechanism, cells within the hypothalamus will release inhibiting hormones. So we will have somatotropin releasing hormone, inhibiting hormone, mammotropin inhibiting hormone, gonadotropin releasing inhibiting hormone. Sometimes we call those statins. So those will inhibit secretions from the hypophysis. What happens when you have a tumor of the hypophysis? When the glands of the hypophysis have tumor and they grow, they have cancerous tissue, they grow, they produce excess hormones. Specifically two cells that are of importance here. We have those that produce the vasopressin. Vasopressin, that is the paraventricular and also supraoptic nuclei. Those ones might produce excess vasopressin. So because of excess vasopressin, we'll have a lot of water. Diuresis. We'll have diabetes insipidus. So with the damage, so we'll have diabetes insipidus, where you have frequent passage of urine. And then growth hormone deficiency. If there's damage to the growth hormone cells, then you have dwarfism. People are very short stature, dwarfs. And then if you have excess growth hormone, before 20 years, usually the hypophyseal plate closes by 20 years. So if the hormone occurs before 20 years, then the hypophyseal plate continues to grow, the bones become very long. Then you end up with gigantism. Very tall people, 8 feet tall, very tall people. But if after the hypophyseal plate has closed and we have excess production of the hormone, then we have acromegaly. The bones become very large, very thick. We have the bone, the face becomes very thick. The skin becomes very thick when you have those excessive production. So these are some of the disorders that can occur associated with the hypophysis. This is the hypophysis. We can note here the 3 cell types. We have these cells, these are basophilic cells. Note that the cells are arranged in a cord, they're in cord. And in between these cords, we have sinusoidal capillaries with some little connective tissue supporting the blood vessels. The orange staining cells are acidophils. orange staining cells are acidophils. And then these other cells which do not take up the stain are the chromophobes. Chromophobes form 50% of the population. So we can notice here the acidophils, and basophils. Acidophils and basophils. This has been stained with orange G. In between that, we have capillaries that are sinusoidal. Here, notice the cells are arranged in a cluster. So cells are arranged either in a cord or a cluster. In this part, notice the acidophils, and all these are chromophobes. Chromophobes. They do not, the cytoplasm is not staining with acidic or basic dyes. And these are the basophils. Here, notice the cells are arranged in a cluster. In a cluster. And in between this, we have the capillaries. Just to show the chromophobes with H and E, notice the acidophils deep staining, the chromophobes not picking up any stain, and basophils basic dyes because it contains a lot of endoplasmic protein. This is the pituitary gland, the neurohypophysis. This is where oxytocin is stored and released, and oxytocin is stored in the form of herring bodies. This we refer to as herring bodies, Herring. Apart from determination of the neurons from the hypothalamus, from the supraoptic and the paraventricular nucleus, we also have pituitary. Pituitary are glial cells. Pituitary are glial cells because this is nerve tissue. Neurohypophysis is an extension of the diencephalon, so it is nerve tissue, and therefore we have some pituitary, which are glial cells. So that is about the hypophysis and hypothalamus. The pineal gland, we say, is P-shaped. That's why it's called pineal. It's in the roof of the third ventricle, connected by a pineal stalk to the brain. We have a pineal stalk to the brain, and we have pineal recess, pineal depression, and the commission, posterior commission, and also pineal recess. That's where it's located. For the structure, we have a dense connective tissue capsule, just like what we have talked about. But this tissue, because it's attached to the brain, continues on with the leptomeninges, that is the dura and the pia mater. The capsule penetrates by form of septa into the organ, giving it a supportive framework. The parenchyma usually contains pituitary, pinealocytes, and astrocytes. Pinealocytes and astrocytes. Now the parenchyma has a lot of blood vessels because the blood is supposed to transport the hormone that is released to the perivascular space. In old age, after puberty, the pineal gland starts to have congregations, what we refer to as the pineal sun, or corpora amarcea, the pineal gland, pineal sun. The pinealocytes are pale staining, and they have a lot of processes. We talked about them having stellate in shape with a lot of processes. And these processes they penetrate into some what we call canaliculi. These are very narrow ducts. very narrow duct. Processes project into this narrow duct. These narrow ducts are thought to be channels for the transport of the hormone, melatonin. The predominant organelles that we have here, what they secrete is indole amines. Indole amines. So we have mitochondria, right endoplasmic reticulum as predominant, and then Golgi apparatus. We also have smooth endoplasmic reticulum, centriole, and lysosome. But the predominant one here is right endoplasmic reticulum and mitochondria. Apart from this, we have, of course, microtubules for the intracellular transport. The secretory granules contain melatonin, and this melatonin is produced by neural stimulation. This is from the suprachiasmatic nucleus, which is usually referred as the biological clock. So during the darkness, the suprachiasmatic nucleus melatonin is produced in the darkness. So this is what we are talking about in terms of very close to the capillaries, and then we have the processes. This is just a section which will be looking at these slides specifically. Look at the blood vessels, then we have the pinealocytes come very close to the blood vessels. Some of their processes come close to the blood vessels. The others are the gliocells. This is the stalk that connects the pineal gland to the brain. They have the nuda commissure. And then we have in the adult and also after puberty, we have the pineal sun. So when you look at the pineal gland, you should be able to identify the pineal sun. What will be the function of melatonin? We have said melatonin, usually when you have light, you want this increased intensity of light in the retina. From the retina, some of the neurons end up at the suprachiasmatic nucleus, which we have said is the biological clock. So from the suprachiasmatic nucleus, some neurons end in the paraventricular nucleus in the brain. These ones usually are the autonomic nervous system. Autonomic nervous system. From here, the neurons go to the spinal cord, and then the superior cervical ganglia, that is sympathetic nervous system. And from this superior cervical ganglia, the neurons then stimulate the pineal gland to reduce the amount of melatonin. So when you have an increase in light, there's reduction in melatonin. So melatonin is produced during darkness. What will be the functions of melatonin? Mainly to regulate sleep-wake cycle. Sleep-wake cycle. Occasionally, when you have traveling over long distance, many hours, and you're traveling east, you will have a jet lag. That jet lag is because of problems of melatonin. So to be able to now regulate your body, you take melatonin tablets because you have not slept for a long flight. It's also very important in inhibiting gonadotropin releasing hormone. Gonadotropin releasing hormone is usually a liberine that stimulates the hypophysis so that you can have release of luteinizing hormone and follicle stimulating hormone. So if we have very low melatonin levels, then that inhibition is stopped. So we have more gonadotropin releasing hormone, we have precocious puberty. The female comes to puberty very early, at a very early age. If we have very high levels of melatonin, then we have delayed puberty because there's a lot of inhibition of gonadotropin releasing hormone, and therefore inhibition of the release of luteinizing hormone and follicle stimulating hormones. So the follicle stimulating hormones, which are supposed to stimulate the ovary to start the cycle, now will be reduced, and that's why you have delayed puberty. So this normally is very important, not very important in man, but very important also in animals because of seasonal breeding. Seasonal breeding. In the males, it also regulates epididymal function. Epididymal function, which is very important in the maturation of spermatozoa. Maturation of the spermatozoa. So it will inhibit release of testosterone, and therefore again delayed puberty if we have very high levels. If you have very low levels, then again what will happen is somebody comes to puberty very early because testosterone will be produced at an early stage. So these are the central endocrine organs. Our class was supposed to be 1 hour. I will now invite any questions. You'll have to reschedule overviews for the remaining parts. Any questions? You can now ask your questions. Put it in the chat. Class reps, are you supposed to be going to another class now? Nothing?
No.
Dental?
No.
Physiotherapy?
We have a class at 11.
Okay, so we can continue to 11 instead.
No.
Consensus? We agree on to continue to 11?
Yes.
Thank you. So this is we have dealt with the central, and you can see how they influence the peripheral endocrine organs. How they influence peripheral endocrine organs. Okay, before we leave that, let me just make comments on this. Somebody wants us to talk about parvocellular. Now, parvo means small. Parvo means small. So the nuclei, the cell bodies of some secretory neurons, they do not transmit any impulse, but they secrete hormones, are small in size, and therefore they are classified as parvocellular neurons. And these ones here are within the dorsomedialis, ventromedialis, the infundibular, and the tubal nucleus of the hypothalamus. The parvocellular neurons have very short axons. The axons terminate in the primary capillary plexus, where they release the releasing hormones, which we talked about. So every hormone released by the pituitary, there is a releasing hormone which stimulates its production. So that is released at the median. The primary capillary plexus is at the median eminence. That's why I said at the area of the median eminence, the blood vessels, the capillaries there do not have a blood-brain barrier. Once the hormone has been released to the primary capillary plexus, it is transported to a secondary capillary plexus in the adenohypophysis. Any blood vessel that joins two capillary plexus is what we call a portal system. This is a portal system joining the hypothalamus and the hypophysis. That's why we call it hypothalamo-hypophyseal portal system. At the secondary capillary plexus, the releasing hormones are now released to the cells. And those cells are the acidophils and the basophils. The specific target for each of those cells depends on the releasing hormone, because they have receptors for those releasing hormones. So if it is a follicle-stimulating hormone, gonadotropin hormone will only stimulate those cells that will produce follicle-stimulating hormone and luteinizing hormone. That is the gonadotropin. If it is a growth hormone, the growth hormone releasing hormone will only act on the growth hormone cells, the somatotrophs. So that's what we're talking about in terms of parvocellular. Magno are the large cell bodies that will produce oxytocin and vasopressin. I've talked about that, and I've talked about pars liberalis, intermedia, and distalis. Now, for pars liberalis, intermedia, and distalis, the Rathke's code, when it comes in contact with the diverticulum from the diencephalon, the floor of the diencephalon, a part of it comes to envelope the infundibulum. That is the stop. And that is what we call pars liberalis. Pars liberalis. And then at the part where the neural part and the glandular part are meeting, usually the glandular tissue mixes up with the neural part. And that's what we're calling it pars intermedia. And then the rest of purely glandular tissue is what we call pars distalis. Fine, if there are any questions again, we will continue looking at them. So we've seen the effect of hypothalamus, the hypophysis, and now regulation of the peripheral endocrine organs. One of the peripheral endocrine organs is the thyroid organ. The thyroid organ originates from the floor of the third pharyngeal pouch. Floor of the third pharyngeal pouch. This is normally marked in the tongue by a depression forming the anterior 2/3 of the tongue and the posterior 2/3 of 1/3 of the tongue, that we refer to as foramen cecum. So the endodermal cells grow downwards, they originate downwards, and come to lie in the neck region, over the thyroid cartilage. At the distal part, they form two lobes, they divide to form two lobes, joined by a very small area that we refer to as the isthmus. The connection to the tongue usually disappears. Occasionally, however, we might have some remnants of the thyroid gland in the tongue. Sometimes we call thyroglossal cysts or thyroglossal duct that continue on to the thyroid gland. Can you stop talking, please? Mute your microphone. So the thyroid gland is covered by a connective capsule. It's covered by a connective tissue capsule, just like the other organ. So it's located over C5, T1, that's the gross anatomy, covered by infrahyoid muscles, supplied by the superior thyroid artery, inferior thyroid artery, and the isthmus is covered by thyroid ima from thyrocervical trunk. Can you please stop, mute your microphone, whoever is not muted? For the structure, we have a capsule, we have the stromal disconnected tissue generally at the top, supporting blood vessels, nerves, and lymphatics. The parenchyma consists of thyroid follicles. So the functional unit of the thyroid is a follicle. Between those follicles, we call that parafollicular area, which contains parafollicular cells. The follicles are lined by an epithelia that vary in shape. It can be simple cuboidal to low columnar, depending on the functional status of the thyroid. We have a very well-developed capillary network around the follicles because the hormone is to be transported by blood. The cells, they are the thyrocyte, that say that cuboidal or columnar in shape, and their main function is synthesis and also storage of T3 T cells. The cells synthesize the hormone. The hormone is stored in the form of the colloid, as a thyroglobulin. That's the colloid. Between the follicles and also sometimes embedded between the follicular cells, we have C cells, what we call C cells, and parafollicular cells. Parafollicular cells secrete a hormone called calcitonin. Calcitonin lowers the calcium levels in blood. It lowers calcium levels in blood by promoting deposition of calcium in the bone, by promoting reabsorption, secretion of calcium in the kidney, and by inhibiting the absorption of calcium in the digestive tract. So in that way, you are able to lower the calcium levels in blood. This is a thyroid gland. This large connective tissue area is what we call the septa, and the septa contain blood vessels. The septa then penetrates into the organ, dividing it into lobes and lobules. So each of these is a lobule. In each of the lobules, we have a follicle. So this is the functional unit of the thyroid gland. And the follicle contains colloid, thyroglobulin colloid, and is lined by simple cuboidal to low columnar, depending on the functional status. In an inactive thyroid gland, there is an increase in the amount of colloid because the hormone is stored as thyroglobulin in an active gland. In an hyperactive gland, the colloid is then taken in by endocytosis. The colloid is taken in by endocytosis, and the hormone T3, T4 is released into the blood, and there's recirculation of the iodine and also the globulin part. So that way the colloid is removed from the center. The cells therefore become almost columnar, like I've said, low columnar. So this is a hyperactive thyroid gland. The other one is inactive thyroid gland. Around the follicle, this is a follicle. Around the follicle we have blood vessels, a very well-developed capillary network comprising of fenestrated capillaries. Between the follicles, Between the follicles, we have parafollicular cells that secrete calcitonin. So this is an inactive thyroid. Notice the cells are cuboidal in shape, a very large colloid containing thyroglobulin. Notice again cuboidal in shape, connective tissue surrounding the follicle, which is a functional unit, and this connective tissue contains a very well-developed capillary network that surrounds the follicle. And in between those follicles, we have parafollicular cells. Again, notice an inactive follicle, but just to demonstrate the capillary network. What appears as red here, these are capillaries that form a very well-developed network around the follicle, specifically for the transport of the hormone, and also transport of the calcitonin produced by the parafollicular cells. These are parafollicular cells. At high magnification, note the capillaries. Note a high content of colloid because it's inactive. Now, this has been stained to demonstrate calcitonin. So what appears as brown, those are cells that contain calcitonin. Those will be the parafollicular cells. They can either be between the follicles and also embedded between the follicular cells. So those we refer to as C cells. C cells secreting calcitonin. What can go wrong? Sometimes we have a remnant of the connection, some remnant within the trunk or within the neck, upper neck region, or part of the verticula that was eventually to form the thyroid gland. So we have thyroglossal cysts. It can be in the tongue. But we can also have iodine deficiency. How is thyroxine formed? Thyroxine, first we have the protein synthesis, the globulin. Globulin is synthesized by rough endoplasmic reticulum. It is transported to the Golgi apparatus, starting through the Golgi apparatus with some carbohydrate moieties. Then that is at the apical part of the cell, we have iodination of tyrosine moieties, iodination of the tyrosine. And before that, we have the iodide uptake by the cell. The iodide is then converted to iodine, mainly at the apical. Sometimes they say at the apical part of the cell. Some people say it's within the lumen. Some literature is not completely clear. The iodine, then we have iodination of the tyrosine moiety by thyroid peroxidase enzyme. So that forms what we refer to as monoiodotyrosine. And also diiodotyrosine. So after this iodination, 3 or 1 iodine, we then have coupling. And coupling is where we have a combination of monoiodothyronine and diiodothyronine forming triiodothyronine, T3. Or you have diiodothyronine having 2 iodine. The 2 of them can combine to form T4, tetraiodothyronine. So these are the enzymes which are stored within the colloid as thyroglobulin. During the release of the enzyme is taken up. Again, coupling and also the formation of the monoiodothyronine and diiodothyronine is acted by thyroid peroxidase enzyme. During the uptake of the enzyme, the colloid is taken up by endocytosis. That is endocytosis. It combines with a lysosome. So lysosomes are very well developed. Within the lysosome, we have proteases, enzyme proteases that breaks down the protein tyrosine so that the T3 and T4 are released. T3 and T4 are released. And then the globulin part, the protein part now is taken up to the liver. Sometimes we also have within the liver, the enzyme can be broken down to form monoiodothyronine and diiodothyronine within the liver of the kidney. T3 is the most active part, and that is very important for metabolism of the body. Thyroxine is very important in metabolism. So when you have iodine deficiency, the gland will try to grow, the cells will try to grow bigger, become bigger, to try to produce as much hormone as possible. Because of that, there is enlargement of the thyroid gland that we normally see as goiter. We can have hypothyroidism, too much production of the hormone T3, T4, what we call Graves' disease. And in hypothyroidism, there is a high heart hypertension, and we also have rapid palpitation of the heart, rapid beating of the heart, and intolerance to temperature. Or we can have less production of the thyroid hormone, hypothyroidism. So in hypothyroidism, remember we have very low thyroid hormone in circulation. So there is no R, Hashimoto's, no R in Hashimoto's. So we have the condition which is called myxoedema. And usually, because there is metabolic rate is very low, the person is intolerant to temperature, cannot withstand temperature because it's very low, body is very low temperatures. And the person is inactive also. The other gland that is very closely associated with the thyroid is parathyroid. Parathyroids are two, we have said superior and inferior parathyroid. The superior parathyroid originates from the fourth pharyngeal pouch, so it's endodermal. It is dragged along by the superior parathyroid goes on to the thyroid gland. As the thyroid gland also grows, it moves on together with the thyroid gland and ends up to lie very close to the thyroid. The inferior parathyroids originate from the third pharyngeal pouch, close to where the thymus originates. So during the migration of the thymus, it tugs along the thymus and eventually comes to lie inferior within the thyroid gland, the capsule of the thyroid gland. So that is the origin of the two glands. The parathyroid can appear individually, the four parathyroids. The parathyroids can appear individually, covered by a capsule, or they are embedded within the capsule of the thyroid gland. It comprises of three cell types. The principal cell type, also called chief cells, are the cells that produce the hormone parathyroid hormone. They are epithelial arrangement, usually columnar or polygonal in shape. columnar or polygonal shape. We have free ribosomes, large Golgi apparatus, secretory granules, some lipid droplets, and some glycogen. That is when it is active, when it's producing the hormone, parathyroid hormone. So those are T cells, slightly pale staining because of lipids, basophilic because of ribosomes. The other cell types are clear cells. And clear cells are thought to be a form of T cells that have excess glycogen. This can be demonstrated with the PAS staining, periodic acid staining. They are also thought to be degranulated cells that have shadowed the hormone, parathyroid hormone. The other cell types are oxyphils. Oxyphil cells are polygonal, large, small nucleus, the mitochondria, glycogen granules are also present. Free ribosomes are in the cytoplasm. And these appear at puberty and increase with age. Because of that, they are thought to be degranulated cells, but they are also called oncogenes. Oxyphils, the cytoplasm is full of mitochondria, and therefore the oxyphil are deeper staining, basophilic in nature. The parathyroid gland also contain adipocytes, white fat, embedded amongst these other cells. What is the functions of the parathyroid? One, production of parathyroid hormone. And the parathyroid hormone increases the calcium levels in blood and therefore maintains calcium levels in blood. It increases calcium levels in blood in three ways. One, it can promote osteoclastic activity, osteoclast. So there is resorption of bone, calcium from the bone by osteoclasts. Two, it increases reabsorption of calcium in the kidney. Three, it increases absorption of calcium in the digestive tract. So overall, it increases the calcium levels in blood. So what happens when we have excess parathyroid production? If you have a tumor of the parathyroid gland, it means there is excess calcium. There will be too much deposition within the bones. You have too much reabsorption from the bones if you have parathyroidism. Too much calcium. The bones will become very weak. So there is pain in the bones. There will be deposition of sometimes calcium because there is too much of it in the kidney. So you can end up with kidney stones. What about when you have hypoparathyroidism? Sometimes when they remove the thyroid gland, they might remove parathyroid accidentally. Then there is very low calcium levels in blood, and therefore you end up with muscle cramps because calcium is very important for contraction of the muscles. Apart from muscle cramps, you will also end up with the tetanic contractions, tetanic contractions of the muscles. So that's what we have as some of the disorders of the parathyroid gland in case either there is less production or a tumor stimulating overproduction. The thyroid gland is not regulated by the hypophysis or hypothalamus. The functioning of the thyroid gland is regulated by the amount of calcium in blood. If there is high calcium in blood, then calcitonin takes in to reduce the calcium. If there is low calcium in blood, parathyroid then increase calcium levels in blood in the three ways I talked about here. This is the thyroid gland on the right. This parathyroid gland, like I said, they are very closely associated. They have their own separate capsule. Here we have two cell types. You look at the cytoplasm, the cells with the deeper stain in cytoplasm. These ones here are the oxyphils. Oxyphils have deeper stain in cytoplasm because of a lot of mitochondria. The cells that are light stained cytoplasm, very light stained, these ones are chief cells. Chief cells and also clear cells. Chief cells and clear cells. And notice the blood vessels, therefore that we refer to as the definitive cortex. Definitive cortex. So by the third year, we are able to identify all the three layers of the cortex. And we have covered that when we are dealing with the immune mechanism. For the endocrine ovary, we are going to deal with this again when we are dealing with the reproductive system. But just to mention, that the primordial follicles usually are lined by